Thank you. All right, I want you guys to imagine that you're a radiologist. It's 8 a.m., first case of the day, you have 100 cases on your list, you're feeling optimistic. History, rule out a diagnosis. Not very helpful. Okay, so you dig through your EMR, you go through Epic, it takes you 3, 4, 5 minutes, and you piece together the history and you find out that the patient has cirrhosis, they have a history of cancer in the past, they had a 2-centimeter liver lesion 3 months ago. Took you a while to get there, but you're there. Check the protocol, biphasic liver. For the radiologist in the crowd, wrong protocol. Okay, protocol based on incomplete information. No delayed phase, so it's limited to evaluate for liver cancer, which is the main question here. Okay, let's just dictate. Limited study, next field, 3-centimeter liver lesion, next field, cholelithiasis, next field, splenomegaly. Oh man, it looks like I'm off by a field. I gotta cut and paste, another few minutes. Okay, conclusion. Let's just dictate the conclusion. Liver lesion increased in size. Wait, what's threshold growth in LIRADS again? I have to look it up, look up the table, find the right, interpret it. I'm just gonna call it indeterminate. Let's just do that, and it's about time for my second coffee of the morning. Feels like an inconvenience. But now imagine you're the patient that has a history of cancer. You had a scan 5 days ago and you're anxious to get your results. You get a notification. Your result is ready. You feel a pit in your stomach. You click on the link and this is what you see. Your anxiety is replaced with confusion. What does that mean? What does indeterminate liver lesion even mean? These arterial enhancing foci. A limited exam, I drove 2 hours to get there. What does that mean? All of this makes you feel even worse. And this is unfortunately the reality for many patients today. So I'm Rajesh Bhayana. I'm a radiologist in Toronto and the AI lead at Toronto JDMI. So we serve UHN, Sinai, and Women's College. I just want to say thanks for having me here today. An excellent list of speakers. So honored to be here. My disclosures, including the platform mentioned, teaching platform navigating radiology. So when we think of LLMs and Gen AI, this has been covered a few times today, but some of these cool tools come to mind, like ChatGPT, Claude, Notebook LM, and other cool tools. But 99% of our job as radiologists looks like this. Okay, we're sitting there at a computer, protocoling, dictating reports, etc. So my talk is going to focus on this. Specifically, we'll touch on the current landscape of AI in radiology, some of which has been touched on a couple times today, how we can actually leverage LLMs, and then rather than focus on future potential, I want to talk about the clinical impact today. What can we actually do right now? So let's first set the stage. You've all likely seen this meme many times. But why has this prediction been wrong? Or actually, some haven't seen the meme, I guess. So others who have like, why has this prediction been wrong? Or is it actually wrong? Because, I know Ujin said this earlier, according to Dario Amodei, Anthropic's CEO, AI has gotten better than radiologists at doing scans. Interesting verb. And what the radiologist actually does is they kind of just walk the patient through the scan and they kind of just talk to the patient. So clearly Dario hasn't met many radiologists if he thinks our strength is talking to patients. But it's kind of comforting that such big names in AI have absolutely no idea what we do. Recent radiology villain number 2, Woojin also mentioned this as well, Mitchell Katz, CEO of NYC Health and Hospitals, made a very poorly worded statement with big backlash from the radiology community. To throw him a bone, he was referring in the subtext narrowly to first reads of x-rays and mammo. And there are some flashes of preliminary reports and second readers for mammo. But, as mentioned a few times today, we all know that autonomous AI in radiology outside of extremely narrow use cases is pretty far off. So in addition to overselling this and choosing his words very poorly, Mitch missed the forest for the trees. This tweet more accurately noted that, in fact, radiology jobs are thriving and demand is increasing. Andrej Karpathy, OpenAI co-founder and LLM thought leader, composed a reply that went even more viral. He said, radiology was, in fact, not the best example to pick in 2016. It's too multifaceted and too high risk. Karpathy cites Jevons paradox, stating that increased efficiency tends to increase consumption over time. So, if radiologists are sped up by AI or made more efficient, more demand will follow. The topic even made it to the New York Times, including how AI has been more friend than foe for radiologists. So I think we need to update that famous meme with 2026 and beyond, where radiologists can use supervised self-driving to get to work and have AI help them with every single step of the workflow and every report in a supervised way. But how? So this figure from my 2024 review on LLMs in radiology outlines the radiology workflow on the outside in blue, from requisition all the way through to report. And in red, the areas that LLMs can help. Just a couple years later now, this was published over 2 years ago, LLMs are already impacting almost every one of these steps. In research we see it, but also in commercial products. But before we dive into some of these steps where it impacts our workflow today, I'll take a step back to reintroduce LLMs and how we can actually use them clinically. So everyone and their mother, it's been mentioned a few times today, has interacted with LLMs through chatbots, like ChatGPT. These are commercial applications that are built on top of LLMs or large language models, and of course, these can never be used or should never be used with actual clinical or sensitive data. The underlying LLMs themselves, though, like GPT 5.5 as of yesterday, Gemini 3, etc., those are giant neural networks, and when you access them the correct way, you can use them securely inside your own healthcare applications. So for instance, at UHN, we have access to Azure, where we can access these models, frontier models, in a secure way. So how LLMs work is beyond the focus here, and most of you already know, but just to simplify and level set, these are large neural networks that are trained on massive amounts of data to predict the next word or token in a sequence. They are then tuned to behave in helpful ways. So the best way to mentally frame this knowledge, or their knowledge that they have, is that they compress the internet's knowledge or information into their parameters during pre-training, but it's a lossy compression. So their baseline knowledge can be thought of as a hazy recollection of what they've seen. That's why we see hallucinations with some of those imaging examples that were shown earlier, for example. And that analogy is courtesy of Andrej Karpathy. And that knowledge has improved over time. Even that lossy compression has improved over time in medical domains, including in radiology. But it's still limited. These models can hallucinate and confabulate, sometimes producing confident but incorrect statements. We know that general LLMs are not optimized for narrow medical tasks out of box. For example, this radiology study showed that when trying to assign BI-RADS categories to reports, general chatbots do very poorly, which is not unexpected. It's not surprising without any optimization of these general LLMs. Clinical tasks often need optimization, and this basic framework has been presented many times, so I won't belabor the point. But again, think of LLMs as having a hazy memory or hazy recollection of the entire internet. To optimize for a task, you can start with prompt engineering, i.e. giving an LLM very clear, detailed instructions and all of the context/knowledge it needs to perform a task. And this works surprisingly very, very well for many tasks, and we'll show that in a bit. And as the models get better and better, more often this can become enough for certain tasks. If you need to add a larger amount of knowledge, tools like techniques like RAG or retrieval augmented generation is best, pulling the most important pieces of knowledge into context or chunks of data into context, i.e. bringing that knowledge into focus. And if you need to better align the model's behavior or style with your particular use case, that's where fine-tuning comes in, which involves further tuning your model on multiple labeled examples. Importantly, nowadays, all of these are extremely user-friendly to leverage on these modern platforms, even on platforms like Azure, for instance, that we have access to at the hospital. And these can be used by absolutely anyone. So in general, one major point that I want to make today is to highlight how much the barrier to entry has dropped for developing simple tools. And what that means is that increasingly, the physicians who experience real-world clinical problems can more easily, at least, build tools themselves that can help solve their problems. And we're seeing this more and more and more. George mentioned vibe coding as well, and so again, LLMs are great coders. And with the rise of vibe coding and true agentic coding platforms, like I have a few on the screen there, building these simple tools is really accessible to absolutely anyone. And so to illustrate this brilliant, lovable ad, this is a 10-year-old who typed a prompt to build an AI tutor to help him learn math. And Lovable built the app, including the front end, API calls, database, everything, and it worked. And he says in the ad, do adults think that this is hard? So AI really does, again, to a degree, democratize simple software, very simple software, by lowering the barrier to entry. It's, again, far from perfect, and we can show examples of that later, but as it continues to improve, it can be and is, to a degree, deflationary on very simple tools that we use day in, day out, outside of medical imaging predominantly, but also potentially inside of medical imaging. And that all sounds amazing, it sounds very cool, but while the marketing makes vibe coding look like this, very cool and easy, in reality, for anything more substantial, it tends to look more like this. The reality is that building good software still involves blood, sweat, tears, and an element of having good taste. Right? You have to build something that people want to use. Vibe coding does make simple functions more accessible. But in healthcare, real systems need, and it's been a topic today, integration, security, and scale. So for fun, before I get into some of the clinical applications that we're using at JDMI and at UHN, I'll show some very simple non-clinical tools that I've created in production just with vibe coding. I'm not a coder or developer by any means. This is a radiology knowledge search. So I used to Google questions when I reported. Then I started to use ChatGPT. And then I realized it just kept agreeing with me. It would say, whatever I said, it would say, you're thinking about this the exact right way. And that's, I'm sure everyone's heard that exact same phrase over and over again. And sometimes the answers are just too general. They're not very specific. So I just made this for my own use when I report. So you can try it with the QR code if you'd like. It uses RAG, has multiple API calls to answer your questions using high-quality models and layers of API calls for reliability, grounded in the best radiology evidence that we have. There are inline references and images, kind of like an open evidence for myself when I report. Beyond text, this is something I'm using to help teach radiology. So on my teaching platform, we have an AI attending with a voice that leverages real-time API. So you can scroll through a case, you can say what you think it is, the findings, diagnosis, etc., and it'll immediately speak back to you, redirect you, and kind of help you along the way to redirect, give guidance, and or teach you. And then this is a fun project I've been working on, vibe coding something called Radlingo. It's kind of like the Duolingo for radiologists. It's a gamified app where you can kind of work through questions. There's daily streaks, trophies, an oral board simulator, etc. But again, the main point I'm trying to make here is that, I'm not a coder. Agentic coding has truly democratized the ability to create some of these simple applications. So for experts with narrow domains like radiologists, you can build tools that solve some of your problems and some of your colleagues' problems in a somewhat efficient way. But these are all web apps. These are not really what we're using for clinical care. So let's pivot to discuss examples of real clinical impact, including what we're working on and doing at JDMI. So back to our diagram. Let's start with clinical history. So clinical history, as you all know, is very critical in imaging. But this is often what we get. Follow-up. What's the primary tumor? We don't know sometimes when we're reporting. Or rule out a diagnosis, my personal favorite. We all know that the same findings can mean different things depending on the clinical context. And this problem is not new. So this JAMA paper at the bottom here is from 1963. So this is an age-old problem in radiology. But using LLMs tapped into clinical notes, we can auto-generate a structured history with the key details that a radiologist actually needs. We only really need a handful of pieces of information when we're reporting. So for oncology imaging, for instance, I can quickly see the primary tumor, tumor markers, any acute symptoms, or any treatment history. So in our paper, using simple prompt instructions only using GPT-4, it extracted the simple information from the chart or from the note very accurately. And this generated histories that were dramatically more complete than the standard of care, admittedly starting from a poor baseline, and radiologists strongly preferred these histories for reporting. So this is a clear example where a pretty straightforward LLM approach can make a big impact over standard of care. There are more complexities, of course, with bringing this to practice, but it promises a big improvement over our current standard of care and what we're doing in practice now. Next, once the requisition is placed, a radiologist needs to protocol that study, i.e. determine how it's going to be done. So protocoling is important. For those unaware, it's how we choose kind of which of the 40 different ways there are to do, say, a CT, abdomen, and pelvis. It's crucial, but it's also very time-consuming. So it's a repetitive process. We go through hundreds of these in a day. It's often done inconsistently across residents, fellows, and staff. And so automating or offloading this task has been a pretty common or hot topic in the literature. But the traditional paradigm has involved, historically, using large amounts of data, labeled data, and that is somewhat inflexible. Models are trained to replicate humans in the past, and you need a lot of data to train them, and they don't adapt quickly when the protocols change or we want to change how we're protocoling, maybe using less oral contrast or introducing new protocols. They're inflexible. So in contrast, one of the greatest strengths of LLMs is their flexibility. So they're explicitly designed to follow instructions. These modern instruction following models are very good at that. So if we were to give an LLM detailed, explicit instructions based on our own institutional guidelines, it might be able to follow them more faithfully than a large heterogeneous group of residents, fellows, and staff, and therefore make us more uniform in how we do things. So I'll spare the detailed methodology. This was recently published in Radiology, but we tested two approaches. We used GPT-4o as the LLM at the time with a very detailed prompt instruction only. So this included a 7-page prompt, over 3,000 tokens, outlining exactly when to choose each protocol. If-then statements, different cancers, all of the details offloading our mental model of how we do this task into the prompt. And then we used GPT-4o with fine-tuning, where we used the same instructions, but the model was trained on additional examples of input histories and output protocols. So we compared these to the originally assigned protocol in practice by the human. So to simplify the results, the LLM with detailed prompting only selected an optimal protocol 96% of the time, outperforming the human protocolers at 88%. And fine-tuning, in our study at least, did not improve performance any further. So this challenges the assumption that you need a large amount of volume, or a large volume of data, I should say, of labeled examples to train these models to do tasks like this for this particular use case. So for this use case with modern instruction-following models, detailed prompting was all we needed to unlock this use case. And so we're using this in practice now. So any CT at TGH or any of the JDMI hospitals, comes into the RIS, sends over to this protocoling application, and we return. This is hosted on Azure in our hospital tenant. And at order entry, sends over, we send back the protocol, urgency levels pre-selected, and any comments. And so this pre-populates the fields in our RIS, so we can just verify these reports. And anecdotally, we're doing a prospective evaluation now, but anecdotally, it used to take me like an hour and a half when I sat at Princess Margaret going through 200. It takes me about 8 or 9 minutes now because it's just a single click workflow. So now let's touch on the most obvious use case. It was touched on briefly by Woojin as well. That can improve our efficiency, and that's reporting tools. So there are many players in this space: Nuance, RadAI, RadPair, and others. And they all offer many, many features. But at the core, they all focus on making us more efficient. Sorting findings, so we don't have to cut and paste and move things around, into structured templates, and generating auto opinions, mentioned earlier, that mirror your individual style. And LLMs do this very, very well. But we talked about also improving quality. For complex clinical reasoning tasks, like let's say assigning LIRADS categories, which I alluded to earlier, where you need to consider so many different features like size, growth, enhancement patterns, etc. General LLMs out of box tend to struggle with this task. So simply predicting the next token isn't a reliable way to predict or calculate these complex scoring systems. So to optimize performance, our group is using a hybrid approach where LLMs handle what they're very good at. They extract all of the features and structured described features in the report in JSON format. Then we apply deterministic rules to that extracted data to reliably assign the RADS categories. And this actually works very well. So for example, in our ORADS MRI work published in Radiology, the hybrid model outperformed the LLM-only approach, as well as originally dictated scores by radiologists. And we're seeing the same with LIRADS, and we're currently working on that. So we're piloting this in practice. We created an application that kind of layers or works on top of our current RiskPACS platform. We worked with the Cancer Digital Intelligence team at Princess Margaret Hospital. It's called AutoRads, and we're piloting this currently and assessing it prospectively in practice. So this is a quick preview. This is what it does. So this is the AutoRads application. It kind of floats above your reporting window. Here I've selected 2 add-ons, so LIRADS and Auto Opinion. Here's the original illustrative unstructured report. So the application will pull that. It'll transform it into a structured report with a Auto Opinion, as well as a LIRADS synoptic report. So the LIRADS synoptic report, to zoom in, is the correct score. It notes and pulls and realizes that there's a threshold growth criteria, which is a major LIRADS criteria. That's something that can change management and is often missed in practice. Now, again, to the earlier point, structuring a report and generating an auto opinion are the core efficiency features that these dictation platforms offer. And now, that same functionality can be built extremely efficiently with tools like this for a tiny fraction of the cost. And so just for fun, to illustrate, I vibe coded this web app. This is just for my own personal use, and it's not ready for clinical use or anything, but it does all the same things. Medical speech recognition using DeepGram Medical, which is, there's an API for medical dictation with high accuracy. And then all of the AI functions are integrated. So this is just built in a few hours. This is not going to be used by anyone. It's not going to replace any tools, but it's illustrative of the change the point that I'm trying to make of the democratization of being able to produce tools like this. So lastly, once a report is verified, patients are going to see it, and they often see it before they see their doctor. Okay, and this is the last kind of part of this pathway that I wanted to talk about. This can be confusing and anxiety-provoking, as I illustrated with the kind of opening scenario. So there are some players in this space that are helping. So Scanslated and Pocket Health, they spoke earlier today. They help by defining key terms and kind of trying to define certain parts of reports for patients, and that can be very helpful, but not yet really fully unleashing the power of LLMs. LLMs, we know, are very good at simplifying the language in radiology reports to a lower or to the suggested grade level. But in earlier papers, at least, critical errors occurred in a very large proportion. These are earlier papers. Now, more recently, this one came out in late 2025. This one used Llama 3.3, published in Radiology. And this paper, I think, really highlighted the power of patient-friendly reports. If you look at some of the stats that they cite, improve simplifying the reports, reduce patient reading time, all of these things are selling the patient-friendly report. But they still noted severe factual errors in 4%. So the problem here is still largely the same. And common across all the papers I showed and most of the papers in the literature is that they're all using the same kind of way of doing it. There's a heterogeneous group of reports. They vary quite a bit. Renal stones, MRI for a complex cervical cancer, they're all very different. And they're feeding it into a single general LLM using a one-size-fits-all approach and having AI create a simplified report from scratch, starting with nothing. But patient-friendly reports did not start with AI. Okay, this is not a new thing, it's been done. In fact, at our hospital, our urologists years ago found that their patients who were getting their prostate MRIs often did not understand their prostate MRI reports. So Dr. Nathan Perlis, one of our urologists, led efforts to create this patient-friendly report that's on the screen. They worked with patients, they worked with physicians, and worked with consultants to define the language, the format, and the diagrams that would be included to best help the patient. Then they had someone manually sit there and create these reports from the original radiology report and then pilot it in practice. And again, we saw in the previous study, and we're seeing with this one as well, patient-friendly reports tend to work when done appropriately. So they saw that it improved patient understanding, patients found it more useful, and the appointments that they had with the patients, the discussions were able to be more productive and more informed. So that's great, right? We should be doing this for absolutely everybody. But the problem is that this is not scalable. Manually creating these reports for every single patient is just not feasible. So, using the same hybrid approach I referenced earlier very briefly, we automated it. And so now, with a prostate MRI report input, within seconds, the system will generate the patient-friendly PDF, automatically placing the lesion in the correct location on the diagram using the same language. This is working with very high accuracy, and we're prospectively assessing this now as well. So you can imagine that this same optimization approach could extend naturally to other complex systems like LIRADS, TIRADS, pancreatic cancer staging. And ultimately, this provides an avenue to create specialized types of patient-friendly reports that are more accurate, useful, richer for these specific indications, and less likely to need human intervention. So we've covered a lot of applications, clinical applications that can impact care today, and the ability is there to impact care today. And it's been mentioned again and again, and I feel like, going towards the end of the day, we'll repeat some of the same ideas, but the capability is not the barrier to using these in practice. It's everything that comes with implementation, change management, integration, it's the word of the day. With the rise of AI agents, it's also been mentioned a couple times, things like OpenClaw, and now models with computer use. You can imagine how giving these models access to the right environments and the right data can help, or can eventually might help overcome some of these integration barriers if done safely. So with that, I'll end the way I started. So now imagine you're a radiologist. It's 8 a.m. next Monday. You sit down to report. The auto history gives you all the key details that you need, including the primary tumor and treatment history. The AI selected the correct protocol for you, so you have all the images you need. You dictate in free text, the findings sort themselves, the auto opinion appears on the screen, and the LIRADS is scored correctly. It flagged threshold growth, something that I probably might have missed myself if it didn't. It's a better quality report. Now, imagine again you're that patient. You had imaging, you're anxious to get your results, you get a notification, your result is ready. You feel a pit in your stomach. You click on the link, and this is what you see. It's a structured report. You click on the Summary for Patients button, and it automatically generates an accurate, patient-friendly report that makes it easy to understand. That includes a simple diagram that you can see. Unfortunately, the cancer is back, but now you know, and you can shift your focus to preparing for the next step. Thanks for having me. Appreciate the invite and the time, and happy to answer any questions. Thanks.